So now let's talk about the different other leads that we have not mentioned so far. So we spoke about the bipolar leads, leads 1, 2, and 3. Previously, I may have mentioned them as unipolar leads, but correction error. Leads 1, 2, and 3 are actually bipolar leads. Now, unipolar leads, what does it basically mean? The direction of the current can only travel in one direction, so it's unipolar. So it's one that goes in one direction. So augmented leads, AVF, AVR, and AVL are basically the unipolar leads that we're going to be looking at now. Now on the screen you have the main image that I want you to focus on is the top left. So we know leads 1, 2, and 3. Leads 1 goes from negative right arm to positive left arm, and then leads 2 go from negative right arm to positive left leg, and leads 3 goes from negative left arm to a positive. So overall, from the previous few slides, you should have understood that there is an overall positive deflection in these 3 leads. Now let's look at the augmented leads. The augmented leads, AVF, goes downwards from the center of the heart downwards. So you would possibly expect, since the voltage or the current is flowing in the same direction as the heart's the conduction system of the heart, you would most likely end up getting a positive deflection, a very big positive deflection in the R wave, just like in lead 2. And then you would have a very small negative deflection in the S wave, since it's very small, and you would also have a very small negative deflection in the Q wave, mainly a big positive R wave, just like in lead 2. Lead AVF and lead 2 almost are very good to look for in ventricular hypertrophies and things like this. Lead 3 as well. Now AVL, on the other hand, augmented lead left, the current flows from the center towards the positive left arm. So now in this one, the main key point is, remember the diagram from the previous. So initially we had so on the right you can see the GIF, and you know the SA node comes down and then it goes into the bundle of His through the septae, where it goes initially. When you look more closely, the vector or the electrical spreads out towards the right side of the right atrium and the right ventricle first, and then downwards, and then back up to the sides of the ventricle. So you know the first bit here is the Q wave. It's always a negative deflection, and then you have a positive R wave deflection, or the positive slope of the R wave. Then you have a down slope, still positive deflection. This is where the is spreading out through the walls, and then finally you have a S wave, which is when the electrical impulse gets to the edges or the peripheries of the ventricles, which is denoted by the negative deflection here. The reason why is because it's going more close to the negative. Now in AVL, you can see that since the direction of the current in our leads, i.e. not the heart current, the actual current in the actual leads is going in that direction, the S wave would be projected as the biggest and the R wave would actually be quite small. AVR, on the other hand, is completely opposite direction. It's going in completely the opposite direction. Since your heart's conduction is going downwards, where my mouse is pointed in this direction, since yours going, the electrical impulse is going the opposite way. So according to my little box here, since when electrical impulse goes towards the opposite side, as a current travels towards a negative pole, the waveform usually deflects mostly downwards. So in AVR, what you would end up seeing is a negative deflection of the R wave and a positive deflection of the S wave. So it's completely opposite. So reciprocal, or the mirror image of what you would see in leads 2. Now that's a very key important. AVR and AVO. In AVO you would see a big negative S wave, but in AVR you would see a big negative R wave. Now let's look at the different views of the walls. So in this part, so you have simply the only things I want you to look at in this. I know there is a lot of diagrams, there is a lot of illustrations, but this is simply an ECG of a normal, healthy patient. So the only thing I want you to look at is leads 1, 2, 3, AVR, AVO, and AVF. So let's look at leads 1. So we have a normal ECG where there's a P wave. I know it might not be clear to you guys, but there is a P wave here, and then there is what's known as here is a Q wave, and then an R, and then an S wave. Here you can see that the reason why I've put the arrow here is because it represents almost the biphasic. So this is, lead 1, the current is flowing in this direction, and your heart's current is flowing in this direction, so it's almost perpendicular, hence why the waveform produces a biphasic QRS complex. So it's almost the S wave and the R wave is almost equal in size, so it's biphasic. In leads 2, the current is going in the same direction as the heart, so there's a greater positive deflection of R wave, and then the S wave is negative, but it's not so much of a negative. Leads 3, again the same. Now in AVR, we know that since in AVR, you can see on the bottom right of the screen, since the currents in the lead, not your heart in the lead, is going in the opposite direction to how your heart is going, you would see everything in the reciprocal or the mirror image. So it's a negative deflection of the R wave, which is seen here. And then in AVL, since it's going in that direction, there'll be a greater negative S wave deflection. And then in AVF, since it's in the same direction as the heart's conduction system, you're more likely to see exactly what you see in leads 2, almost similar to leads 3 and leads 2. So hopefully now you understand what do you see in leads 1 to AVF on an ECG graph.